Hello and welcome to the Math 135 review problems from Exam 1. I have picked a few of each type and the numbers are next to each problem. I have already started number 3 a little bit ahead of time, but I'll walk you through what I did. So we're trying to solve this by graphing. That was the directions that were on the worksheet. And so the first thing you want to do is solve each of those for y. So subtracting 5x over to the right, dividing everything by -3, which will turn both of these into positive, and we keep them both as fractions. And on this one, we'll add the x over and then divide everything by -2. So that makes this -1/2 x minus 3/2. Okay, so we're going to graph the red line first. And remember, when you solve a system, you're looking for the intersection point if it exists. So when we go to graph this, I'm going to need to plot as many points as I possibly can. And then I'm going to try to use my straight edge or tool here to draw a straight line. So let's do this red equation first. So at 2/3, that's a little bit above a half. And our slope is 5/3. So up, and you go to the same spot on the next spot. So up 1, 2, 3, 4, 5 over 1, 2, 3. And then I'm also going to go down and left because that's the opposite of up and right. So down 1, 2, 3, 4, 5, left 1, 2, 3. And I don't know if that point's going to stay, so we want to make sure it stays. And then we're going to connect those using our, you would normally use a straight edge or a ruler, and then you would draw it, but I'm going to use a shape here of a line. So we want to try to make sure that this is the best that we can get through all 3 points. And it really would be important to use a straight edge or another piece of paper on the test to help you draw nice straight lines, because you don't want to miss the intersection point because your lines are sloppy. And this is not wanting to move. Hang on just a second. Let's undo that line and do a different one. There we go. This is a little bit harder than drawing a line with your actual pencil. Okay, that goes through all 3 points. All right, and then I'm going to make that line red and a little bit bolder. So let's do that. There we go. So now let's do the second line. So this time we're going to have a blue line. So let's go ahead and let's go ahead and plot the points first because we need our points before we can plot them. So let's go to our blue color and we're going to plot -3/2 is -1.5. So I'm going to put a point there. And then we're going down and right. So down 1, right 2, down 1, right 2, down 1, right 2, down 1, right 2. I would do that up and left as well. So up 1, left 2, up 1, left 2, up 1, left 2. That should be plenty of points to draw that line. And there we go. So let's make that bolder. Okay, so it looks like we do have an intersection point in this graph, and it happens right here at -1, -1. So that's my solution. So that means this is a consistent system and independent since it has a single solution. And you can check this really quick, especially if you don't know what that looks like it crosses at, if you weren't being careful with your lines. If you set those 2 equations equal to each other from the y equals part, you can actually solve for the x value of that intersection point. So if we were trying to solve this, I'd probably multiply everything by 6 to clear out the fractions. So that'd be 30 divided by 3, that'd be 10x. 12 divided by 3 would be +4. 6 times -1 would be -6 divided by 2 is -3x. 6 times -3 is -18 divided by 2 is -9. I would add over the 3x and subtract the 4, And notice that the x value that we're supposed to cross at is at -1. So if you have that, you can always plug it into one of these to find that it is also a y value of -1. So anytime you think the point you're crossing at looks a little bit off, or it doesn't seem to you that you've got it right, you can always set the two equations here equal to each other and try to solve for that x value. And then the y value you just get by plugging it back in. So that is one way to solve this algebraically and check yourself to make sure your graph is good. Numbers 6 and 9 are next, and these directions said do this however your instructor told you to, essentially. That means you can use either substitution or elimination to solve these. I'm going to use elimination because that seemed to be the method we used the most, and it was the method we used when we were doing the 3x3 or the 3 variable ones. So it seems that it would be probably easier just to know one method. If you like substitution, you can still do substitution. There's nothing wrong with that. So I'm going to rewrite this as 3x minus 2y equals 4 over 6x minus 4y equals 8. And I think I'm going to try to cancel out the y's. So if I multiply this by a -2 on top, that will make that a +4, which will cancel with that. So this would then become -6x plus 4y equals -8. This equation has not changed. So when we add them together, everything cancels out. That means we get 0 equals 0. Anytime you get 0 equals 0, that means that, first of all, anytime all of your x's and y's completely cancel out, that means it's either infinitely many or no solution. The way you determine which one of those it is does the sentence make sense? If 0 equals itself, then that is always true. So that is infinitely many solutions. If you had like 0 equals 5, that would not make sense, and that would be like no solution. And I did not see on the answer key where you had to write the parameterized solutions, so we're not going to fuss around with that for the test. So for this next one, it's a little bit trickier because you have this issue of decimals and fractions. I would clear the decimals and fractions first. Then we can determine how to cancel out a term. So if you multiply everything in this equation by 10 because there's only one decimal place to clear out. First of all, you need to be careful. 10 times 0.5 is 5x. 10 times -0.4y would be -4y, but you also have to multiply 10 times 2, so that makes this 20. For the second one, since it's got one denominator, we want to clear it out. We need to multiply everything by 4. So that would be 20 divided by 4, which is just 5x. 4 times 3 is 12y. And 4 times -5 is -20. I think we can get the x's to cancel out if we multiply this equation down here by -1. So this would be 5x minus 4y equals 20, so the top stays the same. And this is -5x minus 12y equals +20. The x's are going to cancel out. This would be -16y equals 40. Divide both sides by -16. And we do not turn this into a decimal, we just reduce it. So if you can divide both top and bottom by 8, so that would be 5. It's negative over 2. So my y value is -5/2. Now, in a system, you always need an x and a y, or if you're doing a 3 variable, you need an x, y, and z. So we need to plug back in and find the other value. And you can plug back into one of the originals, or if you don't like that they have all the decimals and stuff and fractions and stuff, you can plug into this as long as you were careful when you cleared your fractions and decimals. So this is 5x minus 4 times -5/2 equals 20. This would be 5x, that's +20 divided by 2, so that's +10. Equals 20, subtract the 10, and then you divide by 5 and gets x equals 2. So the ordered pair for this system is 2 for x, -5/2 for y. Okay, the next example that I picked was one of the 3 variable ones, just so we could practice one of those. I usually pick an anchor equation. I'm going to use this one as my anchor. I know that these only have 2 variables, but they're both different, so that doesn't help me as much. So what I'm going to do is stack these so that on each side, the x plus y plus z equals 1 is the top equation. On the left side, I'm going to put 2x minus y equals negative 2, lining up my like columns. On this side, I'm going to put 3y plus z equals 2. You need to determine what variable you're going to cancel out, and you need to be consistent on both sides. I think it's easiest to cancel out y on both sides. That won't be too bad. So on this side, it's already ready to cancel. So we can go ahead and add. This would be 3x plus z, because there's only 1 there, equals negative 1. On this side, we're going to have to multiply this top equation by a negative 3 to make the y's cancel. And remember, you do have to cancel the same variable in each group. Otherwise, you will not eliminate a variable. We're eliminating y completely so that we can just focus on x and z. So this would be negative 3x minus 3y minus 3z equals negative 3, because we multiply it all the way across. And then 3y plus z equals 2 comes down. And this cancels, and that leaves me with negative 3x minus 2z equals negative 1. So now we take these two equations and we stack them as a two-variable equation. So that's 3x plus z equals negative 1 over negative 3x minus 2z equals negative 1. And the x's are already ready to cancel, so we got lucky. So this is 1 minus 2, so that's negative z. Negative 2 plus negative 2 is I wanted to multiply, is negative 2. And then if we divide by the negative, we get z equals 2. Okay, so in our ordered triplet, that's going to be our final answer. We already know that the final spot is a 2, because remember, it's x, y, z. Now we're going to take this 2 and plug it back into either this black equation here or this blue one to find z. I'm going to choose to plug it into this one because I don't want to deal with the negatives. So 3x plus 2 equals negative 1. That's 3x equals negative 3, or x equals negative 1. And then typically I plug back into my anchor equation. So negative 1 plus y plus 2 equals 1. Negative 1 plus 2 is 1, plus y equals 1. And if we subtract over the 1, we get that y equals 0. So our ordered triplet is negative 1, 0, and 2. Okay, for number 14, we are trying to set up the system ourselves and then to solve it. So let's read through what we have. So it says a theater has seating capacity of 900, so that's 900 people who can come to the theater, and they charge $4 for children, $6 for students, and $8 for adults. At a certain screening with full attendance, there was half as many adults as children and students combined. Total receipts were 5,600. How many children attended the show? So we're going to label our 3 groups, because this is a 3-variable one since we have 3 different groups. I'm going to let C be the number of children, which is what we're eventually going to hopefully solve for. So we're going to be very specific on which variables we cancel out so we don't have to do a lot of back substituting. And then S is going to be number of students. And A is going to be number of adults. Okay, so what we know is that this was a full attendance thing, so that if we add all the different types together, how many children, how many students, and how many adults, that should equal the 900 people who attended the theater. We know a little bit about price. We know that $4 per child plus $6 per student plus $8 per adult was equal to 5,600 for total cost, or price I should say. And then there's this middle sentence. It says there were half as many adults as children and students combined. That means that adults equals half of children plus students. Okay, and I'm actually going to adjust this equation because I don't like having the fraction. I'm going to multiply both sides by 2. So that's 2a equals c plus s. And I'm going to adjust it one more time because typically we like all of our variables to be lined up. So that if I move the c over, it'll be negative c, move the s over, so it'll be on this side, plus 2a, and then that would leave 0 on the right side. So I'm going to rewrite those equations over here now with the correct position. So c plus s plus a equals 900. 4c plus 6s plus 8a equals 5,600, and negative c minus s plus 2a equals 0. Now I want you to note that the first and third equation, if we added those together right now, just as they are, the C's and the S's would completely cancel out and we would be able to solve for A. So I'm actually going to do this one a little differently because that's a really nice position to be in and it works out really great for us. So minus C minus S plus 2A equals 0. So if we add those two together, that is 3A equals 900, or adults is 300. Okay? Now I'm going to substitute 300 in for A in equations 1 and 2. The reason I'm doing that is because I'm going to get rid of that variable by substituting in the number, and then I'll be able to solve for C, which is the one we really want. So we're going to have C plus S plus 300 equals 900, and 4C plus 6S plus 8 times 300 equals 5,600. Subtract over the 300, and that gives me C plus S equals 600. This is 2,400. If we subtract it over, that would be 3,200. And then I am not going to, it's easier to cancel out the C's here just by using a -4, but I'm not really caring about the number of students. I specifically want to know the number of children. So I'm going to cancel out the S's. So I'm going to multiply this top equation by -6. So that would then make it, given some arrows for directions, that would make it -6C minus 6S, and then that's going to be -3,600. This is 4C plus 6S equals 3,200. That gives me -2C equals -400. If I divide by -2, I finally get that C equals 200 children. Now obviously I could figure out the other group because 200 and 300 is 500, so there's 400 students left over since there were 900 total people, but I didn't care about that specifically because of the way the words were in the word problem. So they only wanted the number of children. Okay, so this takes us into the chapter 3 parts. So I picked number 21. This is graphing, and it's hard for it to stay on the same picture. It's graphing a linear inequality. So we're going to be working on this one next. Let me get that centered up there. So typically what I tell you to do for a linear inequality is I would graph these just like lines. You have to ask though if the line is going to be dashed or solid. Dashed only gets done when you have a not an equal to, so in other words just a greater than or a less than, and you use a solid line when you have the equal to bar included. So all of these are going to be solid lines. And then remember the shading is if you've solved it for y equals mx plus b, it's pretty easy just to look at the y-intercept and determine if you're shading greater than or less than, so above or below that. And then we have to determine from that what is going to be the feasible region. That's where all of the highlighted parts would be overlapping. And then from there, we want to label our corner points. So that's all the things that the directions said to do for number 21. So I'm going to solve this first inequality for y by taking that x and adding it over. So that's going to be x minus 5 over here. Divide everything by 2. So that's going to be 1/2 x minus 5 over 2. Okay, let's go ahead and graph that one. So -5 over 2 is -2.5, and then my slope is 1 over 2. So up 1 over 2, 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 and I'm going to do that in the other direction as well. The more points, the merrier. So down 1 over 2, down 1 over 2, down 1 over 2, down 1 over 2, and one more time. Okay, so I'm going to use my line feature to draw that in. It's easier to line it up if you got more points. It's about as close as I'm going to be able to get it. It didn't like that. Well, we're pretty close. So let's make that a black line. Okay. And then this was, before we go on, this was greater than or equal to, so we need to be shading from the y-intercept above. So if you look at your y-intercept, let me get my pen. Here's the y-intercept. We're supposed to be shading above. So notice I'm just going to make some marks here that indicates this is above this line. Obviously, it would go up forever, but we don't want this to get too busy. So let's look at our second inequality that we're going to be graphing. So it's already set up as y equals mx plus b, so we just have to graph it. So we need to plot a positive 3 for the y-intercept, so 1, 2, 3. And this one has a nice slope of up 1 over 1. So that's just going in a diagonal since it's positive slope. And these are not parallel lines. They actually are almost going to meet, but it happens off the graph. That's not going to matter so much because we're going to have some other lines here that are going to cut off the feasible region. So let's get the line on there. And again, I'm just trying to get as close as I can to perfect. Okay, and this one I'm going to talk about the shading in blue this time. So this is less than, so y is less than that whole equation. So remember, you go to your y-intercept and go to the bottom half of the graph. So right now, everything shaded in between my two lines is part of my region, okay? But we do have two more stipulations. X is greater than or equal to 0 is a vertical line right through the y-axis. And it says greater than or equal to, so I'm going to go ahead and label all these. This was y equals x plus 3. This was y equals 1/2 x minus 5/2. And this is x equals 0. And then for this one, we're supposed to be graphing to the right of it. It says greater than, so that means this way. So now we already know that nothing over here could be part of my feasible region because the green is not going to overlap with that. And then the very last piece is the y is greater than or equal to 0. So that is a horizontal line through the x-axis. And we're supposed to be graphing above that one. So it looks like the feasible region is here where all the yellow, pink, green, and blue have been overlapped. So what I like to do at this point, and I know this is hard because I'm going to erase some things, is I'm going to erase out all of those colors because it's quite a mess to look at. And we're going to then just shade in the part that we have. I'm actually going to leave the parts that are in the middle, but we're going to shade in the ones, the one region that is good. If this will let me delete some of these. It's not wanting to let me. There we go. It doesn't like that I want to erase them. There we go. This just cleans it up. On a test, you are more than welcome to use colored pencils or whatever it is you want to use to help you graph, but your final answer should be neater. I know that's hard to accomplish sometimes. These are not deleting out for some reason very well. There we go. Let's see if I can get that last one over here. Nope. Okay. So with my blue pencil, I'm going to shade in the region that actually is my feasible region. So it's going from this line from here to here, down to the origin, across till these connect, and then it moves up. So everything in between here is the part that we would need to shade. And this one is unbounded. Notice that it goes off into this space forever. Now the last part that they wanted you to do was the corner points. So we're going to write those in red. This is the ordered pair 1, 2, 3. So 0, 3. The origin is also a corner point. This is 1, 2, 3, 4, 5, where this connects right here. And then there are no other corner points because there's no other places where two lines intersect because that is unbounded on that side. So that is all for that one. Okay, for the next one, we're going to be doing the whole process. This is the one where they give you the objective function. They give you the inequalities that are your constraints, and then you have to graph that feasible region, shade the correct part, find the corner points, and then you remember you plug them into the objective function to see what the minimum or maximum, depending on what the wording is going to be, or if a minimum or maximum even exists, because sometimes if you have an unbounded region, you may not have that. So for this, we want to make sure we really be really careful and get our corner points correctly. And I'm specifically picking this one because it has one nasty corner point. Last time we had this, we didn't have one like this on the review, but there is one this time. So better just cover it together. So I'm going to solve each of these for y. So I'm going to have negative y is greater than or equal to negative 3x minus 5. If I divide by a negative, remember that flips my inequality and changes all my signs. So that's my first equation. For this one, I would get y is less than or equal to negative x plus 4, and these two are just vertical and horizontal lines. So let's go ahead and see if we can plot these. So at positive 1, 2, 3, 4, 5, I have a point for this first line, and then I'm supposed to go up 3 over 1. So up 3 over 1, up 3 over 1. I could also go down 3, left 1, down 3, left 1, down 3, left 1, all the way down so that I get a nice straight line. Okay, so let's go ahead and connect that line. Best that we can. There we go. Let's make it a little bit bolder. There we go. So that is the line y equals 3x plus 5. And it is sometimes important to label these, especially when your intersections are not nice points. And then let's do our next line. Positive 4 is the y-intercept this time. And it is down 1 and right 1, or up 1 and left 1. So that's just a nice 1-by-1 slope in the negative direction, slope-wise. Okay, so if we graph that line, so this is what I meant by this one has a nasty intersection point. Where these two lines cross, there is not a nice point in the middle. It's kind of out in a fractional area. See right there is not exactly in a nice grid point. So we're going to have to solve for what that corner point is going to be if it's included in our feasible region. So this is y equals negative x plus 4. The other two constraints were vertical and horizontal lines, so those should go quicker. X equals negative 3 is 1, 2, 3, and we go vertically. And I haven't done any shading yet. I should usually do that as I go, but this time I'm just kind of moving along. So this is x equals negative 3, and then y equals negative 1 is a horizontal line through negative 1. Okay. So let's talk about where is the graph going to be shaded. So for this first one, it keeps wanting to jump down. Hang on just a second. There we go. For this first one, the y equals 3x plus 5, we were supposed to be shading less than because it actually flipped when we were doing it. So if you're at your y-intercept, that means we're shading below it. So let's just put a few marks there. And then for the y equals negative x plus 4, that's this line right here. We're supposed to go to the y-intercept again and shade below it. So notice that's on this side of that line. Okay, and then we're supposed to be greater than negative 3, so that means this way. And we're also supposed to be greater than negative 1, so this way. So even though the green's right here, notice that the yellow is not on this side, so it's actually just this little triangle here in the middle. So I'm going to erase some of those highlighting parts that are kind of outliers. This is the easiest way I know how to show you without it being too messy, is to try and use these highlighter functions, because otherwise you're erasing a bunch of stuff over and over again. And this isn't much better, but it works. Oops, I got my line, so let's move that back. Yeah. Okay, so let's get rid of a couple more of those highlighted points. And some stuff down here. And it's, again, not perfect. It's kind of hard to erase these once you've got them there, but I'm going to go ahead and shade what the region is. So notice this right here is where those lines intersect, and the colors would be overlapping down to here. Now, a lot of people will stop at the x-axis, but remember our y line is actually down here at -1. So it's this triangle right in here. Okay, now I can count these corner points down at the bottom pretty easily. This is just over 1, 2, 3, 4, 5, and down 1. So this is the point 5, -1. This one is over 1, 2, 3, and down 1 from the x-axis as well. So this is the point -3, -1. Or no, sorry, it's only 2 over. I miscounted. It's over 1, 2. So it's at -2 because the -3 is here, but we didn't actually have to go that far since this line crossed off early. Let me make that -2 look a little bit better. And then my final point is right here, which is kind of nasty. So the way you find this one is you set these two lines equal to each other. So we say 3x plus 5 equals -x plus 4. Add the x over, subtract the 5 over, and you notice that the x crossing point is at -1/4. Now, unfortunately, we still need the y intercept part of that, the y coordinate. So we can plug it into either one of those equations, but it has to be one of those. So I'm going to plug it into the -x plus 4. So that'd be -1/4 plus 4. So that's 1/4 plus 4. So it's 4 and a fourth. Or you can turn that into an improper fraction, which is what WebAssign usually makes you do. That's 16 plus 1, so that's 17/4. And there's usually a button on your calculator that can do that as well. Okay, so all this work was just to find my feasible region and to find that corner point grouping. So once we get to there, we need to do our chart to see which one of them, or if any, and if you have a closed region like this that's bounded, one of those will be the minimum. We just don't know which one until we plug them in. So you list your corner points, your objective function, which is the one you're trying to minimize or maximize, and then the value you're going to get for each of these. So my corner points were -2, -1, 5, -1, and -1/4, 17/4. Okay, so we're plugging them into, this is the only time we use this equation. It's the one that we plug into. It's the objective function. So up here, 2x minus y. So this would be 2 times -2 minus a -1. So that's -4 plus 1, so that's -3. This would be 2 times 5 minus a -1 again, so that's 10 plus 1, that's 11. And then 2 times -1/4 minus the 17/4. I would not reduce this. I would leave it as -2/4 minus 17/4, because you can add that together and get -19/4. Now, how do you know if that's smaller or bigger than -3? Turn it into a decimal. This is -4.75 if you divide that on your calculator, 19 divided by 4. So since they were asking for the minimum, that is the smallest number here, because -3 is actually more to the right. So this would be, in our final answer that we would write this on the test, would be, we have a minimum value of -4.75 at the ordered pair, -1/4, 17/4. And that is it for that one. Okay, so we're almost at the end of the video. I know this has been very long. The last one that I picked was setting up just the objective function and the constraints. You don't have to solve anything, you just have to write it out. It looks just like the one we had on our quiz. So remember, A part is your variables, you have to define them. B part is your objective function, and you have to tell me if it's max or min. And C part is your constraints. Okay, so let's read through the problem. Deluxe coffee is to be mixed with regular coffee to make at least 50 pounds of a blended coffee. The mixture must contain at least 10 pounds of the deluxe coffee, and deluxe coffee costs $6 per pound, and regular coffee cost I don't know what happened to the rest of my equation. Hang on just a second. There we go. It's regular coffee costs $5 per pound. How many pounds of each kind of coffee should be used to minimize cost? The most important thing to figure out which one is your objective function is to look at what you're minimizing or maximizing. So we are minimizing cost. So that means P or Z, whichever what letter you want to use for your objective function. I usually use Z or P, so I'll use Z. This is going to be our cost, okay? And the other two things we're talking about is deluxe and regular coffee. So X is going to be pounds of deluxe. Y is going to be pounds of regular. That's all done. The objective function should be Z equals something with X and something with Y, but it has to be related to what you're doing. So it's cost. So that's going to be 6X plus 5Y. The constraints usually have to do with at least or at most. You're going to be dealing with inequalities. So if you mix the two together, you have to have at least 50 pounds. So X plus Y is greater than or equal to 50, because at least means 50 or more. The mixture must contain at least 10 of the deluxe. The deluxe is the X, so X has to be greater than or equal to 10. You don't have to put X is greater than or equal to 0 here, since we already know X is greater than or equal to 10, but we do need to establish that we're not using negative pounds of the regular. So usually if you don't already have a constraint that's bigger than 0, we try to make sure we have that listed in there. And that's it. We don't have to actually solve this. So it's just setting up your variables, your objective function, and your constraints. I hope you guys found this video very helpful. If there's any other ones that you still are struggling with, I don't know that I can promise that I can do a video, but I might be able to write something up or at least answer your questions through email. So just make sure you let me know if there's anything you want to know, and I'll be in my office tomorrow from 9:50 to 10:50 in the morning. You're welcome to stop by in IFC 309. I'll see you guys later.